Well, turns out it also has its own language. We're going to pull back the curtain on the secret languages that really power our entire digital world. And by the end of this, you'll know exactly what those cryptic codes. You ever get that feeling that your computer has a mind of its own? Well, turns out it also has its own language. We're going to pull back the curtain on the secret languages that really power our entire digital world. And by the end of this, you'll know exactly what those cryptic codes on your screen are actually trying to tell you.
So, have you ever seen a string of numbers like this? Maybe it popped up in an error message, or you saw it on the back of your router, and you just thought, what on earth am I even looking at? It looks like a secret code, right? Well, it is. It's a language. And believe it or not, you're about to learn how to read it.
All right, here's our game plan for decoding all this. We're going to start with the big problem that computers have to solve. Then we'll dive into the two languages they use to do it, binary and hexadecimal. We'll even learn how to translate between them, and finally, we'll go hunting for where this secret language shows up in your everyday life. Okay, first things first. Why do computers even need a special language in the first place? Well, it all boils down to a really simple physical limitation.
We look at our computers and we see these incredibly complex machines, right? They can create art, connect us with people across the globe, store, our entire lives in photos. But if you could zoom way in, past the processor, past the memory chips, you'd find something almost shockingly simple at its heart. And this is it. This is the big secret. At its most basic, fundamental level, a computer is just a huge collection of millions, even billions, of microscopic switches. And just like the light switch on your wall, each one can only ever be in one of two states, on or off. That's it. There's no dimmer switch, no kinda on.
And because of this simple on-off reality, computers need a language that only has two symbols. So we represent on with the number 1, and we represent off with the number 0. And this, right here, is the foundation of the binary system. It's the native tongue of every single computer on the planet.
So now we know why computers are stuck with this two-digit system. Let's take a look at how it actually works by comparing it to the system that you and I use every single day.
We use what's called the Denary system, or base 10. It's called base 10 for a super obvious reason. We have 10 digits to work with, 0 through 9. When we write our number, each position has a value that's a power of 10. You got the ones place, the tens place, the hundreds place, the drill. We've been doing it our whole lives. Pretty straightforward, right?
Now computers, they use the binary system, or base 2. And I bet you can guess why it's called base 2. Because there are only two digits, 0 and 1. So instead of the place values being powers of 10, they're powers of 2. You have the ones place, then the twos place, the fours place, the eights place, and on, just doubling every single time. And here's the part that's kind of mind-blowing. Absolutely everything, the words in an email, every single color in a photo, the notes in a song, all of it has to be translated into these long strings of zeros and ones before a computer can do anything with it.
Okay, so we've got our world and the computer's world, two different languages. So let's get our hands dirty and see how we can actually translate between them, turning our numbers into the computers and then back again. Going from binary back to our good old Denary system is actually pretty easy. All you do is look at each digit in the binary number. If it's a 1, you just add its place value to your total. If it's a 0, you just ignore it.
Let's walk through this example right here. Say we have the binary number 1011. We've got a 1 in the eights place, so we grab that. We have a 0 in the fours place, so we ignore it. Then a 1 in the twos place, and a 1 in the ones place. So you just add them up. 8 plus 2 plus 1 gives us 11 in our number system. See? Not so scary after all.
So how do we go the other way? Well, it turns out there's this really clever trick using division. You just take your number and divide it by 2. You write down the remainder, it's always going to be a 0 or a 1, and then you take the result of that division and do it again. You just keep going until you get down to 0. Then, the magic part. You read that list of remainders you wrote down from the bottom to the top, and poof, that's your binary number.
And listen, this isn't just some weird party trick. As you can see from this actual exam question, being able to do these conversions by hand is a totally fundamental skill in computer science. It's used from everything from low-level programming to figuring out network problems.
Okay, so binary is great for computers, but let's be honest, for us humans, reading these super long strings of zeros and ones is a total nightmare. It is so easy to mess up. And that's exactly why we came up with a clever shortcut.
And this quote just nails it. The whole goal was to find a system that was easier for us to handle. I mean, can you imagine trying to read or remember or even just type out a 32-digit binary number without making a single mistake? It'd be practically impossible.
And that brings us to the hexadecimal system. Now, this is a base 16 system. You might be wondering, how do you get 16 digits? Simple. We use our normal 0 through 9, and then we just add the letters A, B, C, D, E, and F to represent the values 10 through 15. The whole reason it exists is just to be a more compact, human-friendly way to write down binary.
Now this chart, this is the key to everything. This is our secret decoder ring. The absolute magic of hexadecimal is that one single hex digit can represent a group of exactly 4 binary digits. So instead of writing out 1111 in binary, you can just write F. And that's why it's base 16, by the way. It's not random. 16 is 2 to the power of 4. Which creates this perfect, elegant relationship. It's a truly brilliant shorthand.
So where do we actually run into this stuff? Well, the truth is, you've probably seen it a dozen times today and never even realized what you were looking at. Let's go find some examples out in the wild. First up, error codes. You know when your computer crashes or a program freaks out and it shows you this code that's just a jumble of letters and numbers? That's hexadecimal. And it's not random. It's a memory address, pointing to the exact location in the computer's memory where the problem happened. It helps programmers hunt down and fix bugs. Next, we've got MAC addresses. Every single device that can connect to a network, your phone, your laptop, your smart TV, you name it, has a unique hardware ID called a MAC address, and it's written in hexadecimal. It's basically like a permanent fingerprint for your device on a network. It's how your Wi-Fi router knows exactly where to send that cat video.
And finally, let's talk about modern IP addresses. We're all upgrading to a new system called IPv6, mostly because we were literally running out of addresses for all our new gadgets. But here's the thing. These new addresses are 128 bits long. That is a gigantic binary number. Writing that out would be insane. So, hexadecimal is really the only sane way to do it.
So the next time you see a MAC address or some weird error code, you're not going to see a random string of characters anymore. You'll see a language. You'll see what's really going on under the hood. It really makes you wonder, doesn't it? Now that you can read this secret language, what other